So now we'll get started on the notes for the two-phase method. The first modification that we're going to look at in this set of notes has to do with the first modification that I mentioned in the summary video, which is what to do when the inequality faces the wrong way in your constraints. So here we have one non-standard inequality because this inequality that I've circled is facing the variable side rather than the constant side. So in this example, we're just going to focus on what to do when this happens. And in this case, I've drawn the feasible region for you. So in other words, the solution set to this set of inequalities. I've graphed it for you already. I won't expect you to graph things that look like this, because this is a little bit too complicated. But the main reason for graphing it is just to point out that the origin is not part of this feasible region. And therefore, we won't be able to use the ordinary simplex method to start with because the simplex method won't know where to go from this origin to get to the next corner. So unfortunately, what we have to do is we have to get into phase one, which is what gets us into the feasible region. And I'll talk about the series of steps that we'll need to take to do that. And then phase two will just be to proceed by the ordinary simplex method. So here's what we do in phase one. So first let's talk about how to set up a simplex tableau for a problem like this one. So we're going to do the same thing that we have been doing for the ordinary constraints and for the objective function. So if you want, you can pause the video and read carefully through this. I'm going to go pretty quickly over it, but I think it is good to read through at some point. So notice that for the ordinary looking constraints, we need to add that slack variable because we have something like x1 plus x2 needs to be less than or equal to 40. Now, if the left side is less than 40, then it's less than 40 by some amount, and I'll call that amount S2. So by adding whatever slack there is in the initial inequality to the left side, I can balance the equation and turn it into an equality like that. Now, unfortunately, for the other kind of constraint, so for the new constraint that faces the wrong way, I have something like x1 plus 2x2 is bigger than or equal to 24. Now, in this case, the left-hand side is bigger than the right-hand side. And therefore, we need to take some surplus away from the left side in order to get it to balance with the right side. And for that reason, we will be subtracting a variable rather than adding one. So these are called surplus variables because we're taking away the surplus that lives on the left-hand side initially in order to get it to balance with the right-hand side, which gives us 24. So that's the main new thing. Whenever your inequalities face the wrong way, you need to subtract the excess that lives on the left-hand side rather than adding the slack. So if the inequality faces the left side, we'll be subtracting a surplus variable. If the inequality faces the right side, then we'll be continuing to just add a slack variable like we have been. Okay, so that's what we're going to do initially. And then we can form the initial matrix. The corresponding matrix would look like this. This is exactly what you would expect from the previous lecture, except that this time notice that we have a surplus variable. And that surplus variable, that S1, is going to have a -1 coefficient. And the way that we're going to decide whether we've made it to the feasible region is we need to see whether any of our variables have negative values. So notice that if I read off the values from this matrix, I would be deleting the non-basic variables. And if I read off the values of S1 and S2, I would have -S1 is equal to 24 and S2 is equal to 40. But notice that that top equation means that S1 is a negative number, and we can't have that. So we will know that we're in the feasible region whenever we made it so that none of our surplus variables have negative values. So the last part of phase one is to pivot so that we no longer have negative values on our surplus variables. But unfortunately, the pivoting rules are a little bit different here. They're not super different, but they're a little bit different. Now we're trying to fix this negative value here. We don't like the fact that our surplus variable has a negative value. So we start with the position of that -1, and we look to the left of it in that row. So look to the left of the -1 and you find the largest positive value that exists to the left here. And in this case, the largest positive value is this 2. That tells you the pivot column. So we would know that this is the pivot column because this gives us the largest value, the largest positive value to the left of my -1. Now we're only looking in the -1 row for these values. So I'm just comparing this +1 and this +2, and I choose the larger of the two to give me my pivot column. And then once we have our pivot column, thankfully, finding the pivot row is using the same rules that we have been using. So I would again compute these quotients like we have been. You take the far right number and then divide by the positive number that lives in your pivot column. So this would be a 24/2, the next one would be a 40/1, and you choose the smaller of these like we have been choosing to give us our pivot our pivot row. So now we found our pivot row and our pivot column, and our intersection gives us the pivot. So this 2 is going to be the pivot, and then we pivot like we normally would. So we turn that pivot into a 1 by using the division row operation, and then we zero out the rest of the entries in that column. So that is phase 1. Phase 2 is the ordinary simplex method. So notice that after pivoting, this is what our matrix looks like. And if you look at this matrix and read off the value of your variables, notice that S1 was originally -24 up above, but now think about what the value of S1 is now. So if I were to read off the value of S1 from this matrix, what would it be? Well, because S1 is a non-basic column, the value of S1 given by this matrix would be 0. And therefore, we're now in the feasible region. This is no longer a negative answer, and so we're done with that phase 1 step. So because S1 is equal to 0, we are ready to proceed with the ordinary simplex method. And I'm not going to go through these steps again. This is just the ordinary simplex method that we've been using. So you look for the largest negative indicator. That's the one that you focus on. That gives you your pivot column. To find the pivot row, you compute the quotients, and then you pivot until you're done with all of your negative indicators. And then once all of the negative indicators are gone, you can just read off the solution from your final simplex tableau. It would give you this solution. So we've already done all of the phase 2 stuff. Phase 2 is just the ordinary simplex method like we've been talking about. The only new stuff is that we need to adapt our strategy a little bit at the beginning of the problem. Here there are really 2 new things. One is that if you have a constraint that faces the wrong way, you need to subtract a surplus variable rather than adding a slack variable. And then the second thing that you need to do is change your pivoting rules a little bit. To find the pivot column, you always start with the -1 that you're trying to eliminate, and you look to its left to find the largest positive value. And the largest positive value to the left of that -1 that you're trying to fix will tell you what your pivot column has to be. So we'll do an example of that here immediately. So let's look at example 1. So here it says, solve this linear programming problem. Our first goal is going to be to set up the initial simplex tableau. So I like to rearrange the objective function so that all of the variables appear on the left side. So that would give me a -3x1 minus a 2x2 plus p equals 0. P is what we're trying to maximize. I also need to take these 2 constraint equations and convert them into equalities. So the first one is standard. So it will just get an ordinary slack variable. So this one would become an x1 plus 5x2 plus our first slack variable is equal to 5. So that's what our first constraint would become. The second constraint, though, this one faces the wrong way. So this one needs a surplus variable. So I would have a 2x1 plus x2 minus a surplus variable equals 12. And notice that just like with slack variables, each one of these constraints will get its own slack or surplus variable. But the difference between them is whether the inequality is facing the left side or the right side. If we have a standard inequality like the top one here, then we would just continue adding an ordinary slack variable. But if the inequality faces the wrong way, then we need to subtract a surplus variable. And now that we've converted these into equalities, what we can do is we can form the initial simplex tableau. So I'll do that over here. We have x1, x2, S1, S2, and then instead of writing the ordinary P column, I'm just going to identify P with this bottom left entry, sorry, the bottom right entry over here. Okay, and now we can add our constraint rows. So the top constraint would be translated like this, and then the second constraint will be translated like this. Notice that because the second constraint used a surplus variable, this has a -1 coefficient for S2. And then for the last row, I'm translating the objective row here. So this would become a -3, a -2, a 0, a 0, and a 0, because remember that I'm suppressing the ordinary P column. So it's typical to just omit P from this matrix altogether and instead identify P with the bottom right value here. But remember that column is technically still just recording these coefficients, or sorry, these constants over here. Okay. So now we need to decide what phase we're in. So I read off the values of my variables. Notice that S2 has a value of -12 from this matrix. Because if I were to read off the values of the variables in this matrix, x1 and x2 would be non-basic, and then I can read off the value of S2, which would be -12. So we do have a negative variable here. In order to fix that, I'll go into phase 1. In phase 1, I look for the negative value that I want to fix, or really I should say the negative coefficient. I look to its left and I find the largest positive value that I can to its left. So in this case, the largest positive value that I can find to its left would be this 2, and that tells me that this first column is the pivot column. Next, in phase 1, I need to find the pivot row. To find the pivot row, I do the ordinary thing, which is to compute these quotients and choose the smallest one. So I'm looking only at this first column, and I'm computing the quotient of the far right value divided by any positive value in this column. So we are only doing this for the positive entries in this column, so that would be this one and this one. You never need to compute quotients for this, for anything in the objective row. You also don't need to compute quotients if you have a 0 or a negative value in this column. So we're only looking for these positive values, the 1 and the 2, and I would compute the quotients. The first quotient is 5/1, which is 5. The second quotient is 12/2, which is 6. And we choose the lesser of these to give us our pivot row. So that means that this is our pivot row, and therefore 1 is our pivot. So we've chosen the pivot 1 according to our phase 1 rules. Next, we would pivot. So to pivot, we would need to turn that 1 into a 1. So this is already a 1. We're happy with that. Next, we need to 0 out the rest of that column. So I want that 2 to be a 0, and I want this -3 to be a 0. So from row 2, I would subtract twice our pivot row. And from row 3, I would add 3 times our pivot row. And in this set of videos, I'm again not going to take the time to do the individual row operations because I think that that would just slow us down a little too much. So I've done all of the row operations on separate scratch paper, and I'm just going to be copying down the result of these row operations. So what I get at the end of this is 1, 5, 1, 0, 5, and then 0, -9, -2, -1, 2. And then 0, 13, 3, 0, 15 for our objective row. Okay, and whenever you're deciding whether you're still in phase 1 or phase 2 or whatever, you should read off the values of the variables again. So remember, we can only continue into phase 2 where we finish getting rid of negative indicators and read off the correct solution if all of our variables are valued at non-negative values. So I need to check to make sure that we've made it to the feasible region. So here x2 is a non-basic variable, s1 is a non-basic variable. It looks like the value of x1 is 5, but unfortunately the value of s2 is still negative. This time it's a -2. So we're actually still in phase 1, because we have that s2 is equal to -2. So we're still in phase 1, and that means we need to be choosing our pivot according to the phase 1 pivoting rules. So I look for the negative coefficient that I want to be fixing. I look to its left, and I look for the most positive value that I can here. But unfortunately, none of these are positive. And that means that we are unable to select a pivot. So if you're ever unable to follow the procedure that's listed up above, that doesn't mean that something has gone wrong. That just means that there is no optimal solution. So our conclusion here is that there is no pivot, and therefore there is no optimal solution. And that's actually our final answer here. So what this means is that in the linear programming problem that we were given at the beginning, there actually is no way to maximize that p-value on the region that we were given. So in our next video, we'll talk about how to apply these phase 1 and phase 2 methods to a problem